certain kind of counting problems. Okay, it's I can call it counting under symmetries. But let's start with very simple questions to get a feel of what we are trying to do. Okay, and also the levels of different people might be different here. Someone might have seen some of it before and so on. So if someone is not understanding something, you can just ask me in between. Okay, that is more very important. Yeah. So let's start with a very simple question. Suppose we have a circle. Okay, and now we have, let's say, um, we have four seats. All right. I'll say it in the language of colors. Let's say we have four colors. One, two, three, four. Okay. Four colors. The question is, if the question is, how many ways are there to color the four seats? You can use one color more than once. Okay. Using the colors. Using the colors. Any color, any number of times. Very simple question. So, what should be the answer to this question? Yeah, anybody wants to come forward and say it? Uh huh. Okay. No, but this question is without symmetries. This question is just how many ways you can fill. Okay. Okay. But all right. So you can say, okay. Uh, no. Let's say so. The colors are R, G, B, yellow. Okay. So no reds. Right. So if there are no reds, then there are 3 to the power 4 ways, which is very clear. Okay. Mm, yeah, one red. Okay. Yes. So if you take these cases in the end, you're just going to get 4 to the power 4. In a. Okay. Yeah. No, this itself will exhaust all the cases. This itself will exhaust. And in fact, this will do, but in fact, you don't need to do like this. You can just say that for every place you have 4 choices. So, I mean, the answer is 4 to the power 4. Just that, yeah. So this is quite a straightforward question, no? All right. Now, if so, this is okay. However, if I change the question slightly to using, yeah, yes, but at the moment we are not considering the different symmetries, meaning that at the moment we are considering all the countings as different, meaning I think maybe you have something like this in mind, RGB yellow, this, and then if we rotate it. But yeah, but at the moment we are considering all these to be the same, or were at least were considering. Now I'm just changing the question so we can see if it changes or not. Okay, so that's where we want to go. We want to say that under rotation, whatever symmetries are created, we will consider all of them to be the same coloring, and then we have to find the answer. That's when it becomes interesting. Right now, we just want to revise our basics. Okay, so now the question is every color only once. Okay, if you use every color only once, so again the answer to this is 4 factorial, provided this is like, I mean, again, this is, we are considering the different symmetries to be different. Okay, then it's 4 factorial. Yes, so only once, and I'll just say it very explicitly. If one coloring can be obtained because there are other symmetries which are not we have not usually studied, so I'll say this very clearly, can be obtained from another by rotation, then they are considered same. Okay, so you're saying that the answer to this should be 4 minus 1 factorial. 4 factor. That's right. That's one way to see it, right? However, um, a slightly different way to see it, not different, but just saying it more mathematically in a way that will generalize, is the following. You separate the two items here. There are two things here. Number one is the different rotations, right? So, how many rotations are there? There are 4 rotations, isn't it? There are 4 rotations. I will label them as follows. One I will call E. E is the identity rotation, which does not do anything. Okay. The next one I will call A. This will be a rotation by 90 degrees. Okay. And then, so for the time being, let us just call it A 2 pi by 4. Then this will be 2 times 2 pi by 4. This denotes the degree of the rotation. Okay. Then 3 times 2 pi. Now, this may look like I'm unnecessarily making it complicated, but we'll see why this will be useful. We have 4 types of rotations. Okay. To begin, now, if these rotations were not in the picture, then how many, then we would have 4 factorial as the answer. Okay. So we will have 4 factorial answers, which I will call here configurations. 4 factorial configurations. Okay. I'll just write a few of them. So here is one configuration. 1, 2, 3, 4. Here is another configuration. I should have kept the same color, but anyways, let's say 4, 1, 2, 3. Then there is another configuration, 3, 4, 1, 2, and so on. Then there are some different configurations. So 4, 2, 1, 3, and so on and so on. We are of course not going to write all of them. There are 24 configurations. Okay. Now what is yes? Mm-hmm. No, we are not considering them to be the same because we are only considering rotations. Yeah. Okay, you are right. I should then. No, 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 no. One second. No, but anti-clockwise rotation. Okay, so that would be reflection. Reflection. Sorry, what was the last thing you said? Uh huh. Like one, two. This one. These two are different because to get from here to here, can you get it by a rotation? I mean by a clockwise rotation. Wait. No, you cannot. Right, you're right. I mean, you cannot get it by any rotation. That's yeah, yeah. So for that, you will need reflections. Okay, but those are also symmetries. In fact, the total symmetries are eight. Four are rotations, and there are one reflection, and they combine to give you something. So they total there are eight, and that forms a group, and so on. But for the time being, we are considering four. And sometimes if they just say symmetries in the question, then you would have to interpret on your own what symmetries they are talking about. For example, if these are people sitting on a table, then of course we are not going to consider reflections because we're not going to go under the table and see, right? But if this is a necklace, then we would have to consider reflections also, right? So then you have to divide by 8. So that you have to interpret if they don't mention it. Okay, so yeah. Hmm. Yes, that's right. And that's exactly what that's a very well known formula, but I'm just trying to explain that. Yeah. And that's n factorial by n. Yeah. No, so what we did earlier, there we were allowed to use one color multiple times. So there has four different, but there we made the question very simple in the sense that we removed the symmetry from the question. Okay, so for example, there we made the question very simple, otherwise it would become very difficult. So there we said that this and this, um confusing myself. This, these and these are different in that question. Okay, if we put, so I'm trying to make it difficult level by level. So now the next thing we'll do is we will allow repetition of color and consider symmetries. Then it will, yes, 4 to the power 4. Yes, that's right. Okay, that's right. Okay, now in this case, it is n factorial by n. Okay, and I mean you can see it in any number of ways, but I'll say it in a specific way, a way which will try to separate the two things. That is, one is the actions that you are performing, and one is the gross set of initial configurations before the action happens. Okay, so now let's see. So what is happening? We have these total 4 factorial configurations without symmetries, which will always be easy to count. Now, what we really want to study is if you start with a particular configuration, then from this configuration, how many other configurations can you reach by performing these actions? Okay, three other, exactly. So I'll just, yeah, say that more clearly in the sense that, so for example, if the word action is not very clear, so for example, if you perform this action on this, then what are you going to get? You will get exactly this, right? So maybe I should say if you perform this action. And these are actually proper words. These are called group actions. But I'm not trying to say use group theory, because then I have to say a lot about group theory, which will take 2-3 classes and 2 classes. We don't have time for that now, at least in this short. Okay, so we're just trying to understand it in an interesting way. We go from here to here by that action. Now, if from here you apply the second action, then you can go to the third one, and so on. Okay, so basically the situation is that from every point you can create three more places where you can go. Okay, from every place there are three more places you can go. And so when you go to the different places, then all these places or all these different configurations are now grouped together, and they are the same. They are considered the same, right? Starting with the configuration, all the different configurations which you can reach, in this case it is exactly 4. No matter where you start with, you can reach 4 different configurations. Okay, in this case, this is the one that I've circled. I'll circle it with a different color. This forms one group. And the good thing is that in fact in this group you can go from anywhere to anywhere directly. If you want to go from here to here, you can go by applying the third action. You can see that. So it's a very good thing, okay, because not just you can go from here to here, but in fact you can go backward, forward in all directions. And that is happening because if you if you take this action, you apply this action, and then you apply this action successively, then you get the third action. And similarly, you can check like 2 rotations is the angle basically adds up, and so on. Okay, so they form a group. This group is called an orbit. And what we are basically trying to study, is how many orbits are there. And because 4 things are getting clubbed together at a time, so we would have to divide the original answer by 4. That's the most basic concept of quotienting. What quotient is, right? You take some collection and you create groups of a certain size, right? Then the new number of groups you will get will be the total by the size of each group, and size of each group is same here. This will not always happen. Okay, that's why the answer is 4 factorial by 4. In general, it will be n factorial by n. Yeah. No, that was just my word. That's not a established word. I just said the set of all the gross set of all considerations. The gross is usually what we say before we apply some subtractions or some netting, right? Like you have a basket and you weigh the basket plus the fruit, and that's a gross weight. Then you remove the basket, something like that. So I meant that before we actually apply the configuration, this set of all configurations, gross set of configurations. Okay, this is basically a set on which this group is acting. Okay, so this is what you get. The answer is n factorial by n. Very, very simple. This group that is formed is not a group in the group theory sense, but it is a motivation. But it is from where the word group theory is taken. Because if you study group theory, you will see that nowhere there are groups are forming. They just have a binary operation, and they just have some rules. You will say, why are they calling them group theory then? What's group? This is the group, because groups are always moving something around, and from one position of something, what are the other position you can go to? We make a group out of them. And similarly, you start with here, then you can go to several. There's another group. So they form any objects, any collection of objects which is moved by these movements. Okay, those collection of objects group, they cluster, they form clusters, and they form groups. And that's why the theory is called group theory, the theory of that. Okay, so now this is very simple. This is very, very simple. Let's make it more complicated. So if we allowed reflections also, then what would happen? Let's just see that for a minute, and then we'll see it for a cube. And then I plan to go to the case in which really what the real matter is, in which actually the colors are not distinct is what it when it becomes difficult, because then each group that is being formed will not have the same size, unfortunately, and that's when it becomes interesting. Okay, so here is my question, that if I have this object, so okay, so we understood till now that knowing the number of symmetries is very very important, right? Knowing the various number of symmetries. The previous question was very easy, just four. That's why we divided by four. Knowing the number of symmetries is very important in these counting problems. Okay, so that's why I'm asking this question. What is, and I'll explain this first, because the word symmetry may not be very clear mathematically what is meant. What is the number of symmetries of this octagon, of a regular octagon? Regular is important here, I believe. But regular, yeah, anyways, regular octagon. So what do I mean first? My thing is that how many ways can you move the octagon around? Keeping it, keeping its, like, this is a solid in the sense that these are solid, this is a solid boundary. You can't twist it and so on. Okay, keeping it as a solid thing, or what is known as a rigid motion in physics. Okay, keeping it as a solid thing in mathematics is called an isometry, but yeah, keeping it as a solid thing, how many ways can you move it around and still be able to place it back on this original position? That will be a symmetry, right? Symmetry is basically how many ways you can move the figure yet keep it where it is. Yes, certainly we can draw a circle. Yeah, that will, maybe I should have drawn that earlier. So remember, you are allowed to pick this octagon up in your hand and move it as well. Means you can move it in 3D space, but at the end of the day, you have to place it back. Okay, now there's importance to what that what meant, but we'll see. We'll get 16. Okay, so can anybody else? I think then Noel knows the answer, but can anybody else explain why it is 16? 8 rotations. So number one thing is that now I will call the rotations in a more measured way before we move into the other motions. So I'll call, this is the basic rotation, the fundamental rotation. The other rotations I will call like this. I'll call it a square. And if you think about roots of unity, it makes sense. But even if you don't think about it, think of it like this. A square is like a composed with a. So a is like a function. A is like a function from these 8 points back to these 8 points, right? So a is a function, to be more explicit, that takes 1 to 2, 2 to 3, 3 to 4, right? 4 to 5, and so on. A is a function, and a square, which is what people will say rotation by 4 pi by 8, rotation by 4 pi by 8. That function is a new function, but it's a composition of a with itself again, isn't it? So that's why it's calling it as a composed with a, or just calling it as a square is not bad. And that helps because then we can use our usual sense of multiplication in this thing, kind of given arithmetic to these motions. And that's where it gets theoretical, so that we can, you can use algebra and all on these objects, okay, in this combinator. And similarly we would have a5 a6. Okay, if someone is not easy with this notation for the time being, they can just use, think of it as rotation by whatever degrees, the different degrees that are there. Okay, by the way, the third thing is that a to the power 8 is just equal to 1. It's just the identity function. I'm not writing it, it's understood here. Okay, then what are the other motions? Oh, sorry, vertices. Oh, you said both. You said both. Right. Okay, so he's saying that there are four reflections. That's four and four, right? So one kind of reflection would be reflection, I'll say reflection about 1 comma 3, 1 comma 5, for example. Then there would be reflection about 2 comma 6. Then there would be reflection about 3 comma 7, and like that, 4 comma 8. Then there would be reflection with respect to the sides, right? 1, 2 comma 5, 6, and so on and so on. You'll get. Now, it's a good exercise, but it's not hard to check that there are no more symmetries. There are no more symmetries. The way we usually prove this is basically you see how much freedom you have, right? You basically think, okay, where I can place the 1. Let's say, for example, I place the 1 to 3. Now, if I place the 1 to 3, then where can I place the 2? Either I can keep it here or I can keep it here. There's nowhere else I can take it. So using that, you put an upper bound. And you even get 16 as the answer. Okay, that's the and that you can write it out if you want to write it more. If someone is not very confident with that, they can try to write it, and if they need to ask me, they can ask me. Okay, on that. So this is a set of all symmetries. Okay, so right now we just counted them. We just counted them. That's all. We just studied the set theoretic nature of it. What's the number of symmetries of the elements of this set? Well, there is no connection. There is no rigid, no nothing, no obstruction. So you can just permute it. So that's answer is 4 factorial. So for a set, the symmetries is just nothing, right? So that's very important because from these sets, by putting relations only, we get these objects. But that's not what we want to do now. So this is there now. We don't just want to study these symmetries. We want to study these symmetries more deeply in the sense that let's take a particular symmetry and see what time. So what do I want to say? Yeah, let's pick a particular symmetry. Let's pick the symmetry A. Okay, if you apply the symmetry on 1, okay, on the point 1, then 1 goes to 2, right? Now if you apply it on 2, then via 2 it goes to 3, and via 3 it goes to 4, and so on. So this symmetry is it's very unique because it kind of the cycle created by the symmetry. Okay, there is only one cycle created by the symmetry, and this is that is the entire set of points. Okay, cycle of A is the entire set, and there is only one cycle. You see what I mean by cycle here? Basically, what are from one point, what are the points you can reach to by repeatedly applying that symmetry? Cycle of the symmetry, that cycle of the symmetry. Now, in general, the symmetry may have many cycles, and it's very important to see the number of cycles. And the cycle theory is really that's how group theorists are in when you study permutations in college, you will be studying them as union of cycles. You will not be studying them as just functions and the bad way we write it in high school. But yeah, it still is there. But yeah, this is cycle of. Let's more interestingly, let's study the cycles. Sorry. Now this is important. So that's why. Ah man, can't write a CL. Sorry. So we have cycles of A square. Can anybody tell me what will be the cycles of A square? Mm-hmm. Mm-hmm. Yes, that's right. Right. 3 to 5. Yeah, that's right. Basically, you'll get all the odd numbers. That's one cycle, right? And the other cycle would be right. Perfect. So this is in, and there's a number theoretic thing that one can say in general, but we will see that when we reach that problem. Right now, we don't want to say everything at once because otherwise we seem very unmotivated. So this action, this A square, this has two cycles. Okay, this has um, Yeah, this has 2 cycles basically. Okay. Now let's do one more, or let's do a few more. It's good because really, see, it's not important to understand these things in a very high theoretical level, but it's very important to get a feel of these things, because later on, if you are studying or some lecture in hi-fi thing, you can understand. Right now, it's important to get a feel of this, because I studied these things and I never felt that I just studied them theoretically. So later, very late, I tried to slow down and learn these things in more detail. Yeah. So, anyways, let's talk about the cycles of a cube. And can anybody does anybody else want to say about this cycles of a cube? Hmm. No, no. Is that another cycle? Wait a minute. Is that so? You go from 1 to 4, then from 4 to 7. From 7, where do you go? Ah, so that's not another cycle. It's the same cycle, right? Yes, that's right. 4 to 2, and you see, basically, you just it's only one cycle again, right? A square has 2 cycles. A cube will only have one cycle. And you can think that this has to do with the coprimality. It has to do with the coprimality of 3 and 8. Okay? We are not, I'm not proving it right now. I'm just saying I want you to observe it. Okay? Let's let's do one more, then it will be more clear. Because this is what, from problem solving perspective, it's very important. For A, yeah? Okay. For a to the power 4, let's see. So I think I'll say this one. So a to the power 4 is very straightforward, right? You basically go from 1 to 5, and then you go 5 to 1. Hmm? Okay, let's see. uh yeah, let's check, because even, yeah, I mean, I don't know it from the head. So let's see. Yeah, I mean, I don't remember it. So let's see. So from 2 to 6, you see, you get 1. Now you see, yes, you're getting 4 cycles in this case, if I am not wrong, right? 3 to 7, and you have 4 to 8. You have 4 cycles. So number of cycles, it has to do with not just the divisibility, I guess, right? Not just the divisibility, because otherwise 4 and 2 would have the same number of cycles, right? Okay. Okay. Okay, let's see. Coprimality is a special case of, is a more general case of divisibility, right? GCD is a more general case of divisibility. But yeah, anyways, let's see. Let's see that. Let's see for 6 and 7. Can anybody quickly tell me what is it for 6? So 1 to 7. There will be 2 cycles, right? So yeah, whatever, you can write it. There will be 2 cycles. Now, if you check for 7, there will only be 1 cycle. It has to do with that. The GCD is the number of cycles. Yeah, that's what I also think. Yeah, and I mean, I know the proof. I thought of a proof, but I will not discuss that now. People can think about it, and we'll need it in a question. We'll need it in a question later. We'll see. But my point was that every action that you have, it creates certain cycles, and all the things, all the elements that are in one cycle are in some sense special. We will see next. Okay, and what, and also understanding which action has how many cycles, okay, will be important for us. So this is there. Now there is general notion of a cycle representation of a permutation, but we'll not discuss it now. Just want to move forward to, okay. Yes. Yeah, no, so the thing is that, if we are seeing from just from the pattern that we are observing, number of cycles, yes, that seems to be the GCD of, so if you have a to the power I, then the number of cycles seems to be the GCD of I and 8, right? It seems to be like that, and that is true. In fact, you can think about it, why it's happening. That can be a good question on its own. Okay, yeah. So, and it will be important. We'll see. Okay, so now um, let's come to this thing. Okay, before moving there, let me do the cue. I want to go back to counting symmetries. Okay, and then we can move forward to using these cycles thing, and then we'll have some new concept of fixed points. Then we'll have to combine all of that in a result. Then we'll have to prove that result, apply it, and prove it. So it's a work, quite a bit of work. Okay, but it's better not to not rush. So yeah, and I could have started with the theorem itself and made you people like just gulp it, but better to see it. So yeah, so now we have this one. I messed up the figure, but anyways, uh, we have this regular cube is what I want. Okay, now my question is again, and this is a it would have occurred in at least hundreds of exams. 1 2 3 4 5 6 7 8. Okay, so what we want to do is we have 6 colors. Okay, 6 colors. Use them only once. Use them only one sec. Yeah, use them only once and color the faces. Color the faces. Faces. So obviously the answer to this will be 6 factorial. How many ways you can do 6 factorial if there are no conditions? 6 faces, 6 colors, simply 6 factorial. Okay. So obviously the question is not this. Again, two colorings symmetric to each other. Okay. So I'll say it more, just say it loosely, which can be obtained, sorry. No, it's a cube. It's a cube. That is another way to say it. Yeah, that's right. Could have said like that. All the faces are non-distinguishable would be another way to say it. Yeah. So, but I'm saying it like this: two colorings will be considered same if they can be obtained by rotation, by some motion, some rigid motion. Yes. Um, yeah, right. But yeah, that's what I will do. Means you can consider your 6 colors to be, yes. In maths, when we say colors, we don't really mean colors. We just mean 6 like this. So R1, R2, R3. Yeah, yeah, that's right. You can do that. But I don't want to use 1, 2, 3, 4 because I've already used it. So yeah, never mind. That's just a notation. Yeah, it's important, but yeah. Let me call it like this. Is that okay? 6 colors. So what will be the answer now? So this is just like the cycle question in distinct colors, but now we have to figure out what do we have to figure out. Let's think about it. Right. So that is 1 sec. So yeah. So basically, huh? Yes. No, so that's actually not he's just saying the principle. Okay. So the principle would be that, see, basically, see, first of all, the again, the gross set of configurations would be 6 factorial, right? There are 6 factorial configurations. Okay, configuration 1, configuration 2, and there are 6 factorial of them. Again, what do we want to do? We want to hit these configurations by motions. Okay, like if you hit this configuration with like if you have this line, which passes through the top plane and the bottom plane, and you rotate it, then you get a different configuration, right? We want to hit these configurations by some motions and then see how many groups are formed. right? Because each group would just contribute to one coloring, right? One type, one answer. Okay, so basically we want to see how many parts will be formed, how many groups will be formed. Okay, basically number of orbits. Wait, am I making a mistake? Am I making a mistake? No, it's right. It's right. Number of orbits. So the number, yeah, yeah. Yes, that will certainly be. So you're trying to figure out the number of motions, or is there a different approach? Okay, so basically you're saying that you fix the top face and the bottom face. All right. Yeah. Okay, but before that, you understand that this word orbit is okay with you? Is okay? Okay. Okay. Ha ha ha. Yes, yes, yes. No, no, that's right. Yeah, that's right. Basically, like from this one, from where else can you go? What others will be considered the same? Like you are already saying one of them. So, what I will write what you're saying. Fix 1, 2, 3, 4, and well, actually not fixed. Basically, when I say this, I mean fix this as a whole piece. Inside it, it will not be fixed, right? So you're fixing the top face and the bottom face. Okay. Or basically, I think what you're saying is you take this axis that passes with the top and the bottom, and then you rotate it, rotate the figure about this axis, right? That's one. Exactly. So if you do that, then how many motions are you going to get? Four motions, because there are four different things. Okay, that's right. So we will record that, and meanwhile we will also say the cycle structure of each of them, because we will have to use that later, and that can also be a good question on its own. Okay, so first is I'll write it like this. One second. So first one will be the identity motion. Okay. What will be the cycle structure of the identity motion? Okay, how many cycles? How many cycles will identity motion, means do nothing motion, have? And how many of each kind? That will not be very useful for us, but we can still say. Yeah, so this is a very silly question. The identity motion is really not doing anything to the faces, right? So it will have 6 cycles, because it's just keeping everything is its cycle, or every face is a cycle on its own. Every face is a cycle on its own, right? So 6 cycles, each of size 1, of course. That's implied from there. This is good. Okay. Now, so this is motion number 1. Now if you take the 90, I'll call it like this, 90-degree rotation by vertical axis. This is what I'll call it, by vertical axis. This is one motion. Let me just write a few of the things that this is doing. It's sending 1 to 4. It is sending 4 to 3, 3 to 2, 2 to 1. Right? So this is already we get a cycle, right, of size 4. And the second one would be 6 to 5, 5 to 8, 8 to 7, and 7 back to 6. Just say it like this. So it has 2 cycles. 4 cycles. Means 2 cycles each of size 4. But we just need the fact that it has 2 cycles for the time being. Yes, that's right. Okay, let's just record a few more, because we won't have to do this all the time later on, because a lot of these motions are kind of similar to each other. Yeah. Okay, what about the other one? What about the 180-degree rotation? About the same thing. By, yeah, so I should have used a different column and better writing. Yeah, but anyways, vertical axis. So can anybody say how, just if you can just say how many cycles will be formed? How many cycles? No, no. Right. So that's one cycle. 4 will go to 2. That's another cycle. That's right. 4 cycles. That's right. 4 cycles. And similarly, you can see that the 270-degree rotation, I guess, will also give 2 cycles. Hmm. No, no, no. Wait, wait, wait. What am I doing? No, it will. Sorry, sorry. And no, but they are different cycles, right? Because 1 is going to 3 and 3 is going to 1. So that's. Uh-huh. Sorry, 1 going to 3. And... Oh, okay, okay. Ha 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 ha. Yeah, yeah. So for this 180-degree thing, see, 1 is going to 3, but then 3 is going back to 1. So this is a cycle, isn't it? So I should not say like this. I should be uniform with my notation. It's like this. One cycle, right? Then another cycle is 4 going to 2 and 2 going back to 4. Another cycle. And like this, you see for the bottom face also you'll get 2 cycles. That's why you get 4 cycles. That is right. That is right. But then though you can say that 1 going to 3 is same as 4 going to 2 also. If you say in that way, isn't it? But yeah. So these are all different. Yeah, I understand you're trying to club them further, which again will be a good equivalence relation later on. But for the time being, I think this is good enough. Yeah. So this and for the 270-degree rotation, it's there'll be 2 cycles. Yeah, yeah, right. Because it's very similar to the first one. Yeah. So again, you can see the GCD thing working out. So for the 270-degree one, it has 2 cycles. 270-degree by vertical axis, it has 2 cycles. Okay. So 270-degree is not same as 90 degrees because with 270-degree, one is going to 2. No, sorry. It is opposite. It's anti-clockwise, something like that, maybe. Right? Yeah, that's right. It's anti-clockwise by 90. So it's not the same because we want to make mean the 90s. But yeah, either ways it will work. Okay. So yeah, one is going to 3, two is going to 1 is going to 2, 3 is going to 2 is going to 3, and 3 is going to 4. So that's one cycle on the top. Bottom also you'll get one cycle. That's easy, easy. Okay. Now what other symmetries are we going to have? Other symmetries. Now we'll not have to write all the cycle structure because we will know more or less what's at least for, let's see. So remember this is about the okay. So I have been saying all this with respect to the vertices by mistake, but this is about the faces, right? It's about the faces. So have we made some fatal mistakes? Yeah, I've been saying it wrong. So this is about the vertices, but the question was about the faces, right? So okay, do we have to change this answer then? Yes. What about the faces? Yes, yes, that's the mistake I made. I think I should have instead number the faces, right? Yeah. I think I mixed up two problems about one about vertices and basically the same questions. Yeah, once you know the this one, you will get that one. But still, so how do we number the faces? That's a little difficult, right? Should we do it? Uh, or wait, I'll do one thing. I will just number the this thing like this only, and then we will just do the faces then intuitively. Okay. So if you take the 90-degree rotation, then 1276 that face is getting moved to 1435, 1465, and that is a better tool. Some net. No, I don't know if a two-dimensional object will reduce, will do justice to it. No, I'm highly doubtful of that. Yeah, because the 3D thing, okay, and soon we'll be reflecting about diagonals and all. So I don't, and I think you cannot bring it to a 2D thing because if you project it, then they are going to intersect, and then it will be, I don't know. Yeah, there would be. But basically, yeah, at the end of the day, this is also the permutations of 1, 2, 3, 4. It's the same, has the same thing. But that's again a difficult. For that, we'll need a theory. That's why we'll need group theory for that, which we don't know right now. Okay, so yeah, that's why group theory is there, because it wants to identify these complicated motions of this, and then we have a icosahedron and all with some more basic things, like somewhat, but then they will intersect, but they will have to intersect in the plane, because it's like when you take the shadow of this in the plane, it will intersect. Non-planar graphs kind of thing. But anyways, yeah. So if we just do it, then it will. If we just take the faces, then it will have 3 cycles, right? Yes. What equivalence? Yes, yes. Then what you are saying, I think that's what you were saying. That's what you were saying, right? Yeah, yeah, yeah. So then you would have 3 cycles, right? Because but the top and the bottom are fixed. The top and the bottom faces are fixed here. So that's the top face is one cycle, the bottom face is another cycle, and the vertical face is moving around is this thing. So 3 cycles. But then this will also have 3 cycles. Okay, you can even write it. It will be 1 3 1 1 1 4. Okay, 2 cycles of size 1 and so on. There's something called cycle index and so on. Just the interesting generative function ideas, but not will not discuss it now. Let's just do this one. So 180-degree rotation would give how many cycles? It will give 4 cycles. No, 4 cycles, right? Because it will take the 180-degree guy. It will take this face 1276. This is my bad notation. It will take this face. Hold on, what am I doing? Yeah, it will take this face to the face 4358, right? And back again. No, this is one. No, no, this is one cycle. No, no, the top face is fixed now. The top face is fixed, so that's another cycle on its own. And the bottom is fixed. That's another cycle on its own. So there are 4 cycles. Okay, so yeah, there are 4 cycles. Yeah, this thing this become a little complicated, but we'll have to do it. I mean, otherwise you can't find the answer. Okay, the cycle, we don't need the cycle thing now, but once we have same colors, once we have like repetition of, you can say allow every color to be used any number of times, 6 colors, but you can use any color any number, then we will have to use the cycle information, and you can really understand, because the cycle information is kind of capturing every permutation on a deeper level, on a computationally deeper level. Okay, so yeah, that's the thing. Right. And then similarly, other symmetries are this rotation about x-axis. So I'll just call this vertical. I'll call this z-axis. Okay. Rotation about x and y-axis. So if you do rotation about x and y-axis, the situation would be exactly the same, right? You would have 4 of them. For each, the situation would be the exact same. I think that's clear with everyone, right? The cycles things you will get exactly the same. Okay, I mean that if you rotate about this one, this x-axis, or if you rotate about the y-axis. Okay, maybe I should make it like this. Situation would be exactly the same, so I'm not writing the cycle structure of that you people can write. So how many are we? Okay, meanwhile we'll have to keep track of how many are we getting. So this will give us 3, this will give us 3, and we have 4 from here, right? This identity is a special case which is common to all. So we get 10. We have 10 motions as of now, but in fact there are many more. What are the others? Yeah, right. Similarly for just one second, y and x-axis. Yes, right. So that will be along the diagonals. So along the main diagonals, I should say. Right. So along or about whatever, about let's just take one diagonal and do, then the others will be clear. Yeah. Yeah, no, but say about the faces. That will be so about this okay, so I have made it bad presentations. I did not remove this before moving forward. One sec. Hmm. Right. So let me just draw one here. Okay. Now, if you so here even I get confused a lot here. So now if the 2 5 is here, now if you're going to rotate, then where are the faces going to go? Tell me that. So if you just rotate about this diagonal 2 5, then as you are saying, this one will go to wait, where will the one go? One will go to 8, right? If you rotate it once by the most smallest rotation, right? One will go to 8. No, no, one cannot go to 3 because if one goes to 3, then where will the 6 go? It will hang in the air. It will not fit on the cube itself again. Yeah. So that's why I am not doing that. So if you send the basically, yeah, if the 1 goes to 8, the 6 will go to 3. 6 will go to 3. Okay. But that is one thing. But basically, what will happen to the faces is you can check. It's easy. Is that this will basically get transformed. This face right here will move to which face? It will move to, I believe, this face. Yes, that looks good, right? Yeah, it moves to that face. Okay. Uh-huh. Oh, yeah, yeah, yeah. So which face I didn't say clearly. It will go to this face 2387. Right? Because and it's not hard to see, but yeah, this one is like you'll have to. I mean, I've I've did these calculations before, so I can say it. Otherwise, it's hard to say it in the class suddenly. But yeah, I have done this before. That's why. So that the thing is that you see this edge. I mean, if they give you on the edges, problem on the coloring the edges and so on, then also it's useful. You this is going right here. This is going right here, right? And this is going here, and this thing. Oh, hold on. So no. The 2 and 5 are fixed. We are just rotating about that diagonal, right? If we're rotating about that diagonal, then yeah. Uh, Wait a minute. So it's confusing. So if you when you flip it over, this face goes to this 1276. This face is there. It goes up in space. Then it goes back. It goes back there. That side. Uh, I am able to see it. Wait a minute. Hold on. Yeah, that's what happens, but I don't know how to convince you people. It seems a little difficult for me. This is when you do the smallest rotation. Now, if you apply that rotation again, and this 2387 moves down to 7856. That's just same thing applied again, right? Basically, you see this. Then this one will become the bottom face if you apply that rotation again about the diagonal. Sorry, it cannot come to. Yeah, that's right. So even here I have made some blunder, right? So even here will directly go back. No, that will not happen, I think. Okay, wait. S- yes. That's definitely correct. Okay, so let me just think about. Just give me 1 second. So, hmm. Hmm. Yes, yes, that's there, but then those similar things are themselves not any simple things that I know of. So just give me 1 second. So, mhm. Okay, yeah, yeah, yeah. That is right. Yes, 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 yes. It will be the top face. I think it will go to the top face. Yeah, that seems more correct. Okay, yeah. Two, three, 1, 2, 3, 4. Yeah, yeah, yeah. This is because the five will never come in the picture. I mean, what you can say mathematically, right? So it should go there. Okay, yeah. So this is what will happen. Okay, roughly. Now, yeah, you can try to convince yourself further, but yeah, this is what will happen roughly. This makes more sense. See, and similarly, the other three faces. Finally, other three other three faces will take care of themselves. Okay. Yes. So there are two cycles. Into two. How many diagonals are there? Six. No, four, right? Into four, right? So there are four of these. Uh, right. There are four of these. So we get four more. We get four more motions. Okay. We get four more. Wait. Eight. Why eight? Eight is what? No, no, but no, no, but for this particular diagonal, if you fix this diagonal 2, 5 and do the motions, if you fix this diagonal and do the motions, then you only get two cycles, each of size 3. Okay. Similarly, if you take the other four, if you take the other four diagonals, right? If you take this, obviously there are four diagonals. If you take the other four diagonals, then you get two. Each will have two. Yeah, but in total you will have 14 motions as of now, right? In total you will have 14 motions. Now we will have because we already had 10, right? And then you have added four, so we'll get 14. And for each of them, we have decided the cycle structure as well. So that is a good thing. Okay. So I mean, in fact, there are other motions that you can think about. So they will be, yeah. So I think the diagonal story is over. Can we do anything else about the diagonal? Is it possible to do anything else about the diagonal? No, but about the diagonal 2, 5 only. Can we do anything else? Is there anything else that we can do? So you can take the 1 to 8. There is really nothing else you can do, right? Okay. So you have to think about the other symmetries now. So there are in fact other symmetries, and that's why it gets complicated. So the other symmetry would be something like this, I believe. So if you just think, you will get. Sorry. No, but then then it will. I don't know, if you fix the non-main diagonal, you will get. Yeah. Yes. Yeah. Yeah. Something like that, right? So you take this plane that is 2, 3, 5, 6, right? You take the plane 2, 3, 5, 6, and you reflect about this. Is that right? Yeah. So in this way, you will get the other symmetry. So let's just do this. Okay. So reflecting about, wait, should I call it reflecting? Yeah. Basically, basically it is rotation of the plane. Yeah, I should say that. That's better. Rotation of 2, 3, 5, 6. Is that right? So if you do that, then what happens? The 2 goes to 3 and they get exchanged, right? So I mean, rotation by 180 degree of force. Otherwise, you're not going to get it on the cube. And the 5 and the 6 get exchanged, right? And what else happens? The 1 goes to 8, right? Sorry? No, no, this is different. So here the 1 is going to go to 8. That you will never get in a rotation about axis, about a um, x-axis, y-axis, or z-axis, about a principal axis, right? You will not get this. So this is different, I believe. Right? This is different, isn't it? Yeah, this is. Yeah, so this plane is a diagonal, is kind of a slanted plane, a slanted plane. So if you rotate this plane by 180 degree, right? If you wait a minute, I'm making a mistake. Making a mistake. One sec. Huh? So if you rotate this plane by, yeah, if you rotate this plane by 180 degrees, right? So this plane. If you rotate this plane by 180 degree, I mean about, of course, in a slanted way only, keeping it slanted and then rotating it. Then the 2 and the 3 will get exchanged, right? The 5 and the 6 will get exchanged, right? The 1 will go, um, the 1 will go to 1, the 1 will go all the way, yeah, it will go all the way to 8, that's right. Yeah, it goes back, it goes to 8, and the 4 goes to 7. This we have not considered this motion as of yet, isn't it? So this again gives you four cycles. Now, how many such planes are there? Because the nature of all of them will be similar. There are, right. I mean, yeah, yeah. So from the top, you have two possibilities, right? No, no, no. So from the top, you have this. Then you can take, yeah, only from the top. So you can just consider four possibilities. That's right. So there are four of these, and each of them will have the same cycle structure, right? So you have four more. So as of now, we have no one, one, 1724. No, that will not be a plane, right? That will become 178. No, yeah, yeah, that's a plane, right? Yeah, that will be a slanted plane. Yeah, no, we have not. Yeah, we have taken that because that will be similar to this one. This 2356 is easy, right? 2356, let's say the 26 is a diagonal of the face 127. Yeah. So like that. So what you are saying is something like this, that only. It's a similar kind of motion. Yeah, it's a similar kind of motion. So it will have the same cycle structure and so on. So there will be four of them like this, right? Because from the top face, you can choose four sides, and from each of those four sides, you can get this kind of a slanting plane. Okay. Sorry, 1 5. So you're saying there are six of them like this, slanting planes. No, but if you pick, see, if I pick 2 3 2 and 3, then I only can pick 6 and 5 to get a slanting plane, right? Similarly, if I pick 2 and 1, then I can only pick 2. I can only pick one more, which is I have to pick 8 and 5. 1 3 6 8. No, but that I think we have already. Okay, so you're saying a reflection about that plane. Yeah, that I think is different. That is a different thing. Yeah, that we'll have to consider those kind of planes. Yeah. So number of parallel lines you can draw on the opposite sides. Yeah, kind of. Yeah, that will kind of give you all the possible. 8 and so 2 to 6, 3 and 5. No, but yeah, yeah, that I've already considered. That is 2, 3, 5, 6. Okay, right, right. 2, 8 and yes, yes. So in this way you will get 4. In this way you'll get 4 of them. Like you take 3 and 4, 3 to 7 and 4 to 6. That's another one. Then you take 1 to 7 and 4 to 8. That's another one. That's the fourth one. You'll get 4 like this. So similarly, you, as Swagato is saying, you'll get the other rotations, so you can take this plane. You can take this plane. Yes, yes. But I'm not sure if the cycle structure will be the same. That's why I'm a little worried, because here you're taking the diagonals. Yeah. So see, the point is, see, we are not trying to count the number of motions only. I'm not like, so we took so much time, but see, that is just counting the number of motions is very simple. Okay, because that is clear. There are 24 of them. You can see, because see, I'll just give a short explanation as to why it is 24. That is not hard, but the fact that we are going into the cycle decomposition of each of them is why it's taking so much time. Otherwise, you can think of some easy way. Like I said in the beginning, you can just think of how much freedom you have for every vertex. So see, for the vertex 1 you have 8 choices. So right. Yeah, right. For you can put it in any of the 8 places. Let's say you pick. Let's say you chose it to put at 8. So let's say you send 1 to 8. Now, once you put one, I mean, I'm taking a permutation of the vertices. I'm taking a motion of the vertices that will give you a motion of the faces also. It's because it's rigid. Everything is not, nothing is getting broken and so on. You send 1 to 8, for example. Once you do that, where are you going to send the 2? If you send 1 to 8, the 2 can either go to 3, it can go to, yeah, right, 5 or 7, because it has to be an edge of 1. And so it has 3 choices. So, and once you do that, you can see, you can just imagine that everything else is just fixed. So there are 24 is the answer. So we are long done with that question in some sense, right? There are 6 factorial by 24. Simple, isn't it? But the thing is that we are trying to understand the cycle decomposition of each of these, which we have almost understood. Now, what I want you people to do, for maybe as a homework you can think of, like there are 6 more, and write the cycle decomposition of them as well. Okay. Then in the next class, we will discuss how to do this, why the cycle decomposition is important, and then how to do it when the faces are not, when the colors are can be used more than once, and for any number of colors. Okay, we will see that the answer will be it will be a polynomial in the number of colors. That we will have to do the next day. Okay, so today we're just counting symmetries and so on. Yeah, I think it's good to not do all of this in one day, because you can get overloaded.